it actually looks like what? 0, 0, 0, B, C, F, right? Again, 0 is it's skew symmetric, so it's got 0 on the diagonal, and then what else? Right. Oh, actually, I'm sorry, guys. I should be showing you a method of calculation, not just guessing here. I mean, so the way to do this more properly is, okay, so A transpose equals to minus A. What's that tell us? It tells us that the A, B, C column, D, E, F column, G, H, I column, notice I transposed it, yeah? And then minus A, minus B, minus C, minus D, minus E, minus F, minus G, minus H, minus I. So there's your component by component. They have to match up, right? So if you look at the diagonals, what do we get? We get A equals to minus A, E equals to minus E, right? I equals to minus I, so therefore A equals to E equals to I equals to 0, as we have already said. I'm just saying that's how you would derive it directly from the definition of skew symmetric, right? Just face the equations, rather than trying to remember factoids that I said 3 weeks ago in class under my breath, at the end of class, in a pinch, whatever, right? And then what else do we have? What are the other equations off diagonal? Yeah, what's that? D equals negative what? Oh, negative B, right? You said that. G equals what? Negative C. And finally, H equals to minus F, right? Where am I getting those? Right? But that, of course, is also the same as this equation, right? And this, matching that, is also the same as this equation, right? And this, matching that, is also the same as that equation. Yowzers. You know, one of the more disturbing aspects of teaching cubbies to 4-year-olds is whenever I sit in their little Sunday school chairs, you know what I'm talking about? Tiny, tiny little chairs. And then you got to stand back up. And at this point in my life, it hurts my knees to stand back up from that position. Like, it's not fun. Because you end up squatting down there a long time, right? And all of a sudden you're kind of stuck there. And when you make noises of pain to stand back up, it makes them happy. Little monsters. Monsters. One of them's the pastor's son. Oh, I tell you. Anyway, so long story short, we have 0, D, G, H, 0, 0, minus D, minus G, minus H. I did the same thing again. I found how to characterize an arbitrary element of the subspace in terms of a minimal set of parameters, right? I've completely used up the defining equations for the subspace and implemented them into the characterization of the element. Once I've done that, then it's easy to see what the basis is. In fact, those minimal parameters that are left over, those are exactly the coordinates with respect to the basis I'm about to write down. So the basis beta here is, again, E12 minus E21, E13 minus E31, E23 minus E32. And we can also read from this calculation that the coordinate vector of A with respect to this beta basis is what? DGH, right? How would you prove that beta is linearly independent here? Why is that still actually kind of logically necessary? Because we don't know before the fact that this is a three-dimensional subspace, right? So yes, this proves it's spanning, but to be logically complete, I should also prove that beta is linearly independent. How would you prove beta is linearly independent? It doesn't take more calculational effort. It just takes you writing a sentence, right? No, well, so suppose the span is equal to 0, right? D times the first vector plus G times the second vector plus H times the third vector equal to 0. That implies, by the calculations on the board, that D, G, and H are 0. Consequently, beta is linearly independent. So I usually just write a sentence. It's clear from the calculations already given that beta is linearly independent. Now, when you write that sentence, beware, if you write it without justification, I might notice. You can try to bluff me. You might get away with it if you've actually written something that constitutes the proof if you look at it. But, I guess to be safe, you could just be like C1 times, here's the safe no bluffing solution. C1 times E1, well, let me just write out 0, 1, 0, minus 1, 0, 0, 0, 0, 0, plus C2 times 0, 0, 1, oh, so much writing, plus C3 that says, what's this matrix? This matrix is exactly if you want to be picky, this detail is missing from my first example, which is a little bit bad. To me, this is a technical detail of that example. If you have done everything else but failed to show linear independence, and what you actually have produced is honestly and linearly independent, I'm maybe not even going to take off a point, depending on the time pressure of the test, right? But on the other hand, if you have given me a linearly dependent set and said it's a basis, I will frown upon that, right? But, yeah. Anyway, I thought it would be good for you guys to see some explicit, just gory subspace calculations, since I ask you tons of these in the homework. Maybe not yet, but soon, right? Yet? Already? I can't remember. I'm about 80% through my solution of the homework. I think what's left for me is the trace identity. You guys have any questions about that? I've talked to some of you individually about conjugation already, right? The complex conjugation. The main point is you can use or prove that if we have A and B in complex n by n matrices, then we define A conjugate, the ijth component of that, to be Aij conjugate. So this is the component-wise complex conjugation, right? And with respect to component-wise complex conjugation of a matrix, you can prove that the conjugate of a sum of two matrices is the sum of the conjugates, and you can also prove that C, a scalar multiple of A times A conjugated, is the conjugate of C times A, and this is for C in the complexes. Now this, in the context that you guys are working on, the set of traceless matrices, the set of matrices whose the sum of A plus A bar is traceless, right? You're asked to show that that's a real subspace, right? So the scalar multiplication you want to look at for that problem with respect to the subspace test is not C a complex number, but C a what? C a real number. Now, if C is a real number, what's that say? That says that C bar is just equal to C again. That the complex conjugate of the number is the number itself. That's a real number. And so this last rule simplifies a bit. For a real number, you can just pull C out, because C bar is equal to C. So that's for a real constant only. For another example that's not terribly relevant to your homework question, if I had I times A and I took the complex conjugate of it, that would give me minus the complex conjugate of A. So like IA complex conjugate, that would be minus A conjugate. Because in between step, that's complex conjugate of I times A, which is, by the way, minus 1. Oh, I'm sorry. I'm an idiot. What's the complex conjugate of I? It's a good thing I wrote down this in between step. Yeah, minus I. An idiot. Duh. So sorry. Oh, no. You guys should stop me. Did you guys have any other questions? I mean, so you guys are done with the homework? No? You just don't have any other questions about it? How many more problems do you guys have left? Half a one? 4? Just the end ones? Skipped around a bit. All right. Well, there's still many hours in the day. I think I hope you guys will make it.
Will you be changing your office hours for A day since you don't have any class that week?
Yeah, I may not be here A day. I'm not sure what my schedule is A day yet. That's a good question. I don't have an answer for it yet. Yeah. What do you guys do?